Hey, good morning to everyone. So welcome to today lectures on DC motors. So in this session we are going to discuss about different type of DC motors, their construction and where we're going to use. So at the end of the session you can able to know what are the different type of DC motors and their performance and where it is suitable in industrial application. Those things you can easily know. Uh, Next, the type of DC motor. So based on how we are going to connect the armature winding and field winding, whether in series or whether in parallel. So based on that, we have three major classification. That is first one shunt motor, then second one series motor, then third one compound motor. Actually, again, the common motor classify into two types, that is a cumulative compound motor and then a differential compound motor. Actually, these two classifications mainly depends on how the field winding which is connected with the armature. Actually, the field winding determine the magnetic flux, and the magnetic flux decide the speed and torque of the DC motor. Okay, so based on that, this classify again to cumulative component and differential compound motor. Yeah, the first one, DC shunt motor. Actually, in DC shunt motor, the field winding, this is nothing but field winding. This is your armature. So we have two brushes in both side of your armature. I'm going to give VDC supply. So input is I mean load, I mean input current. Then that is divided into two. That is shunt field current and armature current. Actually, here in shunt motor, the field winding which is connected parallel with the armature, because the field winding is directly connected across the supply voltage, the field remains almost constant. Okay, so here the using Kirchhoff voltage law, uh, the supply voltage which is equal to back EMF plus armature voltage drop. This is VDC equal to EB plus IRA. Okay, here again the current equation is obtained using Kirchhoff current law. Here the field current which is very small and nearly constant, actually, so the magnetic flux remains constant. So that's why the load current IA, I mean input current, line current equal to armature current plus sun field current. Okay, so again if you multiply the above equation by IA, we will get VDC into IA, EBIA into I square RA. So this is nothing but input power, this is mechanical output power plus the copper loss. So the total input, the electrical input which you are going to give into your electrical motor, which is equal to the mechanical output plus some copper losses. So this is the representation of DC shunt motor. Okay. The next one, that is series motor. Here the field winding, the series field winding, which are connected in series with the armature. Therefore, uh, here the armature current IA, field current, load current, all are equal. Okay, because the same current which all are connected in series, the same current which is flow from series field winding to armature again back to negative. Okay, this is the flow of our series motor. uh, so whenever the load increases, the current also increases, since the field winding carry the same current, so the magnetic flux also increases. So that's why this type of DC motor is preferred for high starting applications like electric trains, crane, elevators, and even traction application. We can prefer this series motor. Okay, so here see that if you use KVL law, the input voltage VDC, that is equal to back EMF plus IA RA plus RSC. The RA is nothing but armature resistance plus RSC is nothing but shunt field resistance. Here both RA and RSC are in series, so we can put together. In previous case, the shunt field resistance is very minimum, but in the case of series field here have some high resistance, that's why we can add with the armature resistance. Similarly, for current equation, here the total line current which is equal to armature current and equal to series, because the same current, for example, if it is have 10 ampere, the 10 ampere flow from plus to again series field, again armature, then come back to negative. So this is the flow of our current. Then again, if you want to know power value, just you multiply with IA. So VDC into IA, then EB into IA, then I square RA plus RSC. This is nothing but input power. This is dedible mechanical output plus this copper losses. So this is the representation of series motor. Next one, this is compound. So in this compound motor, which is combine the advantages of both shunt motor and series motor as well. Actually, based on the connections, we have long shunt motor and short shunt motor. So this is the representation of long shunt because the shunt field winding which is parallel to both series field and commutator. Okay, so the shunt field which is connected across both armature and series field winding. So therefore it provide good starting torque and better speed regulations. Okay, that's why this type of common motor is very suitable for heavy industrial application. Okay, here same, if you want to calculate the VDC and even current and power, same, the input voltage VDC which is equal to EB plus IA into RA plus RSC. Here we consider both armature resistance and series field resistance. This is series field, so this is series field, this is shunt field. Same like a series motor, we can consider this RA plus RSC. So VDC equal to EB plus IA RA plus RSC. Again, if you want to know the current values, that is you can apply KCL at node 1. So this is current case node 1. So this is input current IL, which is divided into two paths. So first path, that is ISC RIA, then this is ISH, shunt field current. So for example, if you have 10 ampere, maybe it will get 8 ampere, it will vary from up to 2 ampere. Okay, so this is the representation of current flow. So the IL equal to IA plus ISH. Here the IA and ISC, I mean armature and series field which are connected in series. So IA equal to ISC. Then the power equation, that is just you can multiply with IA. So VDC into IA, EB into IA, then IA square into RA plus RSC. So this is the input power. This is the mechanical output delivered, then this is nothing but copper loss. So total power input equal to mechanical output plus copper losses. So this is the representation of compound motor long shunt. Then another one, the compound motor short shunt. See that here in the short shunt DC compound motor having both the series field as well as shunt field winding. So this is the compound motor. Here the shunt field which is connected only parallel or across with that armature, across the armature. Okay, so here the series will remain connected in the series with the armature. Here the operating principle which is very similar to your long shunt motor. Here the simple difference is that only the electrical connection. In previous case, that is both, this is parallel across both series field and armature. Here only it is across with that armature. So based depending on the application, either you can use long shunt or short shunt configuration in industries. Okay, here same like the previous one, the input voltage VDC equal to back EMF plus IRA plus IA RSC. If you take IA outside, then RA plus RSC. So this is the voltage equation. Then another one, the current, let us consider node 1, this one. So here the input current, I mean IL line current equal to IA, we split it into two way, that is IA and ISH. See that here the line current equal to series field current. Okay, that's the representation of this. Yeah. Then another one, what is the difference between cumulative and differential compound motor? See that in cumulative compound motor, the series field support the shunt field because both this is series field, this is shunt field, so you can have two winding. So you see that the current direction. So this is like this also like this. So the series will support the shunt field. Therefore, the total flux equals the shunt flux plus series flux. See that, so that's why the total flux equal to shunt flux plus series flux. So in differential common motor, I mean differential, I mean cumulative common motor, if the load increases, the torque also increases. So it will support. Okay. So, but in the case of differential compound motor, the series field winding, see that the current direction like this. In shunt field direction, the current direction like this. So the series field opposes shunt field. Hence, the total flux is equals the shunt flux, which means total flux equal to shunt flux minus series flux. So which will reduce that. So once if you load if you're loading that compound differential compound generator, just you can have a reduction in voltage. Okay, so that is the difference between cumulative and differential component. The based on the connection we can easily understand whether both are in same direction, the flux get added. Here shunt field have flux direction, in series means see that the series will have opposite direction, so the flux get distorted. Flux overall flux get reduced when compared to cumulative compound. That is the difference between cumulative compound motor and differential compound motor. Then next one we are going to discuss about till now we had some different type of motor. So now we're going to discuss about characteristics of DC motor, which helps to know how the speed and torque and everything is going to change with respect to load. Okay, yeah. So the three important characteristics we should know. The first one, that is electrical characteristics. Here that is torque versus armature current. Then the speed versus armature current. Then the third one, mechanical characteristic, that is speed versus armature torque. Yeah, speed versus torque. Okay. Then also remember that we should know two equations, that is speed equal to uh, proportional to back EMF and flux, because if you don't consider this K, so N proportional to EB by pi. So N proportional to back EMF divided by the flux value. Similarly, the torque is proportional to flux and armature current. So which is the two similar two equations we're going to use in various types. Yeah. So this is shunt motor electrical characteristics. Here the armature, torque, TA versus IA. Here in x-axis I'm considering armature current IA in ampere, y-axis that is armature torque in Newton meter. So see that when see that when armature current increases, the torque increases almost linearly. Okay, because the fluxes remain constant, therefore the torque is directly proportional to armature current. So this is the relationship between armature current and a torque. Okay, the next one, that is shunt motor characteristics. Here see that the graph carefully. In x-axis we can have IA and y-axis we can have speed. So even though the armature current increases, the speed decreases only slightly. That's why it is called as constant speed motor. So whatever may be the load, if you're increasing the load gradually, you have slight reduction in speed. See that, for example, 1 ampere, 2, 3, like that. If you vary up to till 10 ampere, we have slight reduction in speed. For example, from rated speed 1500 to now approximately 1460 or 440. So whatever may be the respective of the load, the motor speed always nearly constant. That's why it is considered as a constant speed motor and widely used and preferred in leather textile industries and everywhere. The next one, that is shunt motor mechanical characteristics. See that here this plot again, this the plot is between armature torque and speed. See that the speed, when the torque when TA increases, you can have slight decreases in this speed. Okay, this confirms the excellent and better speed regulation. That's why we can prefer the speed motors in industries. The third one, series motor characteristics. Here, when compared to shunt motor, the series motor behave differently. See that same like x-axis armature current or y-axis armature torque. So before this magnetic saturation, the flux increases with that current. uh, Therefore the torque become proportional to current squared. Okay, the graph become parabolic. See that the graph become parabolic. So once after saturation, the flux become the flux become constant. Okay, hence torque become directly proportional to current. uh, that's why it's produce high starting torque, so we can prefer this type of motor in high starting application, like even traction application, highest lift drilling machines. We can prefer this series motor. Okay, then series motor electrical characteristics. Here we know that when speed decreases as current increases. Okay, because this is going to happen because of high current produce large magnetic flux. Okay, see that here the armature, I mean torque proportional to Ia square leads to TA versus Ia parabola that we discussed in last slide. Okay, so when after saturation, when phi is constant and independent of Ia, hence the curve becomes straight line. Okay, this that like that. So it's look like a parabolic, then it will become straight line. Okay, so this is the electrical characteristics of series motor. Okay, then series motor mechanical characteristics. So from see that from this graph, the small changes in speed, the small changes in speed produce large changes in torque. Okay, so it will give good excellent accelerations. Therefore these type of series motor we can prefer in all electric traction and locomotive applications. Okay, then series motor mechanical characteristics. See that when small changes in the torque, we can have changes in speed. Okay, so this is the mechanical characteristics of series motor. Then compound motor characteristics, that is cumulative compound motor. Here the cumulative compound motor where series motor characteristics are required in addition to load is totally removed. Here the cumulative compound motor which combines starting torque and good speed regulations. Mostly that's why they are used in heavy machine tools, even rolling mills and everywhere. Okay, here uh, in this type of differential common motor, the series field which is weaken the main flux. So when load increases, the flux decreases, which cause speed to increase. Okay, so that's why this motor become unstable. So that's why the differential common motor mainly used for some laboratory experiments. Okay, rather than industrial applications, we can prefer. That is a main drawback of differential common. Yeah, this is the compound overall characteristics of motors, which include compound series, then in that differential compound and cumulative compound, everything. uh, Here the torque is capacity is moderate, so making it suitable for some medium and heavy load applications. Okay, and compound motor characteristics. Here speed versus armature current. Here the speed variation is also some intermediate. The cumulative compound motor maintain better stability. Here we see that when differential motor common motor shows some larger speed variation with respect to load. If we increase the load, we have larger speed variation, but in the case of shunt motor we have good speed because it always constant respective of the load. Yeah. The next one, the performance curve. Uh, Here in this performance curve, uh, which we can easily know how the speed and torque and current, even and efficiency vary with output power. Okay, so in excess we consider output power, in y-axis torque, speed, armature current and efficiency. So observe these four curves. As output power increases, the current increases. See that output increases, the current increases, torque also increases, speed slightly decreases. After rated load, the speed start to decreases. So and efficiency increases. See that efficiency increases until it reaches the maximum near the rated load, then it start to decreases. Therefore, the shunt motor should ideally operate close to its rated load for maximum efficiency. This is for shunt motor performance curve. Then series motor performance curve. See that same like a previous one. Here, whenever the load increases, the automatically speed decreases. With reduce the back EMF, allowing motor to draw additional current and develop a high starting torque. So it's look like a self-adjusting motor. Here, see that. So one thing, please note that in this type of series motor, so always it operate with load. Okay, without load we can't switch on this series motor because the same load current is flow to the series winding, which is very dangerous. Okay. Then third one, comparison of DC motors. See that so in the shunt motor, this is a constant speed motor and we can adjustable. So medium starting torque up to 1.5 times of full load current. So in applications we can prefer this DC shunt motor in drilling and grinding applications and spinning and weaving applications, woodworking machines, because the speed always constant, nearly constant, respective of the. Okay, these are the application of DC shunt motor. Then DC series motor, it is a variable speed motor which can have high starting torque. That's why it can prefer for traction applications, railway cars and cranes, even air compressions, everything we can prefer. So this is the application of DC series motor. Then cumulative compound, this is the combination of two features, that is shunt and series. So it is a variable speed and can have high starting torque. So we can prefer this motor for lift and heist, rolling mills and trolley. We can use this cumulative compound. Okay, thank you all. Thank you.